temperature, alpha drops below beta at this temperature, so our phase diagram would be a one-dimensional diagram along this axis, which would show phase beta until this temperature T alpha beta and phase alpha above it. And there may be more phases on this diagram. They would always be the ones that had the lowest value of the free energy. This is a good point, however, to introduce the concept of metastability. For reasons we'll talk about shortly, particularly when we're talking about structural phase transformations, it's sometimes very difficult to accomplish these. And as a consequence, sometimes you don't get the phase that you think you're going to get because you just kinetically can't make it happen. Sometimes you can get to some other phase. So let's take this phase gamma here. This phase gamma is never the lowest free energy phase. It's above beta here, it's above alpha out here. So in a completely equilibrium situation, you would never see phase gamma. It just wouldn't appear. However, suppose that for whatever reason, it is very difficult for phase beta to form. So even when we go down to low temperature, we just never get phase beta. We just can't get there. It is the preferred phase. It's what the system wants to do, but the system can't get there. So what would our phase diagram look like then? Then at low temperature, our preferred phase would be gamma, because it's preferred to alpha, and beta is an impossible phase, kinetic. As we come up in temperature, alpha would cut through the gamma curve here. So our phase in that case would be gamma up to this temperature, T alpha gamma, and then alpha at higher temperatures. And that's so that we can have these metastable phases introduced if we suppress the formation of the other phases. We can also have metastability, and we almost always do to a certain extent in another sense. Suppose that we have beta and alpha. Here's the temperature at which they transform. Suppose that transformation is difficult. Then this is particularly the case when we take the high temperature phase and try to get the low temperature phase to come out of it. We're in phase alpha, we ride this free energy curve, it should transform to beta right here. Well, very often, particularly if we're talking about solid state transformations, that can be kinetically difficult. And as a consequence, we may find that we're down at this temperature and we're still in the alpha phase. The alpha phase is then called metastable. It wants to transform to beta. It will if a mechanism for transformation presents itself, but still it can often be preserved. So in one-component systems, we do often encounter metastability, which is the persistence of a phase which wants to transform for kinetic reasons. In fact, most of the materials we use on a daily basis are metastable in at least some sense. Something wants to happen to them that hasn't. The Golden Bridge would like to spontaneously oxidize. Fortunately, it hasn't, and hopefully it won't in the next week or two. But these are examples of metastability, which we use all the time in engineering. I can mention here, and I'll mention again later, a second kind of phase transformation that happens, and that's what I call a mutation. You'll find them called second-order transformations. They go by various names. I call them mutations simply because in this kind of transformation, you have a situation in which at a certain temperature, one phase simply becomes another. There's not a question of metastability. There's not a question of a phase transformation. One phase ceases to exist and is replaced by another. The classic examples of that, ferromagnetism. In a potentially ferromagnetic material, all of the atoms have magnetic moments, these little arrows that I've shown here. At high temperature, the state is what we call paramagnetic. These magnetic moments are randomly distributed. I pass through a particular temperature, which is called the Curie point, and all of a sudden these things begin to align. From a crystallographic point of view, there is a dramatic difference, a symmetry difference, between a situation in which these vectors are randomly aligned and a situation in which there is statistical preference for them to align in one direction, no matter how long that is. The minute I establish a preferential direction for those magnetic moments, I have a ferromagnetic material. But the transition from a paramagnetic material to a ferromagnetic material does not have to be dramatic. In fact, it isn't. What happens is we have randomly aligned moments. When we hit the Curie point, there becomes just a statistical tendency for them to become aligned, which gives me a unique axis. As I go down in temperature, they become more and more strongly aligned. But what happens here at the Curie point is that the paramagnetic phase, which has no preferential axis, becomes the ferromagnetic phase, which has a preferential axis. And that becomes stronger and stronger as the temperature goes down. That's an example of a mutation. Other mutations order. If we have a random distribution of beta brass, copper, and zinc over the sites of a BCC lattice, we pass through the ordering transformation, and suddenly it becomes more likely for copper atoms to be here and zinc atoms to be here. That is a change in the crystal structure, crystallography would tell you, from body-centered cubic to cesium chloride. It's a mutation because it happens incrementally at the ordering temperature. The third kind that we see all the time, ferroelectricity, where we have, this is a barium titanate crystal. We have an ion here in the center, which is in the center of the unit cell, so that there's no net dipole moment. We pass through the Curie point for ferroelectricity, and a very slight displacement of that ion occurs spontaneously. As soon as that ion undergoes a slight displacement, I get a dipole moment. That's the phenomenon of ferroelectricity, and it also is a mutation. It happens spontaneously when we pass through a critical temperature. We'll return to that later when we get some examples of these. Okay, let's take phases in a two-component system. Now suppose we have a two-component system, so we have A and B atoms, or 1 and 2, I guess I call them here. Suppose we plot the free energy as a function of the mole fraction of the first component in a two-component system. On this axis over here, we're pure A. We have a certain free energy. As we add in component, you know that initially the free energy decreases with an infinite slope. So if I plot a curve of G versus X, it starts out infinite. It's not quite obvious in this picture, but it starts out vertically bound. As we continue to add component, it will tend to turn around generally, something like this. And if I'm going to form a solution, this curve must be concave up. If we ever go concave down, the solution will become unstable with respect to the division into two elements. So this is what free energy versus X looks like for something that forms a stable solid solution. The chemical potential in that stable solid solution, well, the tangent to the curve at this point is what we call the relative chemical potential. Because if you differentiate G with respect to X, you do not get the chemical potential of component 2. You rather get the difference, chemical potential of 2 minus chemical potential of 1. I'm sorry, I got this backwards because X is the mole. No, X is the mole fraction of 2. This should be X2 because 2 is over here somewhere. All right. What determines the phase that we find in a two-component system? Well, let us suppose that more than one stable phase exists. Here is a plot of the Gibbs free energy as a function of the mole fraction of component B in a two-component system that has component A and component B, and I've drawn this at a given value of the temperature. The condition of equilibrium between these two phases, well, I now have two possibilities. In fact, I have an infinite number of possibilities, the two that stand out. Suppose I'm at this concentration right here, X. One possibility is that, all right, wait a minute, I've got two phases here. I've called this one alpha and this one beta. One of the confusions that people get into in this class, and I want to warn you of immediately, A is a component. Alpha, the designation of an A-rich solution, is not a component, it's a phase. Alpha will have not only a composition, which will include both A and B, it will have, if these are solid phases, it will have a crystal structure. Beta over here will presumably have a different crystal structure. it is a phase that originates over here at the b-axis. A and B are components. Alpha and beta are solutions. Alpha and beta both contain A atoms and B atoms in mole fraction x. So here we have a situation where component A is in the alpha phase when it is pure. As I start adding in B atoms, I get a solid solution, and the free energy curve, if it's stable, it's got to be concave up. Let's say it looks something like this. Over here I have the beta phase. That's the phase that element B has when it's pure. And as I add A, I get a plot of the free energy that varies something like this. At any given value, let's say x, I now have three possibilities. I could have the whole system in the alpha phase. I could have the whole system in the beta phase. This curve would extrapolate up here somewhere. Or I could have a mixture of two phases. I could have alpha and beta simultaneously present. If alpha and beta are simultaneously present, I'll have a composition of the alpha phase and a composition of the beta phase so that the total of them will average the composition of the solution. But what do I get? I'm going to get the situation that gives me the minimum value of the free energy. What I can show is proven in the notes. I'm not going to go through the proof here. I'll just give you the result, which is graphically kind of obvious. Suppose I'm right here, okay? Suppose I consider the free energy I would have if the whole system was in the alpha phase, this value of x. That free energy would be right here. Suppose now I say, well, maybe some of it's in the alpha phase and some of it's in the beta phase. So I'll let the alpha phase be, have this composition and the beta phase that composition, chosen so that they balance out to the composition x. What I can then show is that the free energy of that mixture would be this point right here that I've shown as a dot in the figure, which is above the free energy of pure alpha. You can visualize graphically here and convince yourself that no matter which compositions I choose, if I have a two-phase mixture whose composition averages to x, the free energy of that two-phase mixture is going to move up and down the dotted line at x, and it's going to be an absolute minimum when it touches the alpha curve, which means that the lowest value of the free energy that this thing can have is when I have 100% alpha phase with composition x. Well, now let me take another situation. Suppose now my composition is out here. Now when I take a single phase, alpha, this would be the free energy. Single phase beta would be way up here, so that's obviously not an improvement. But if I take a two-phase mixture and realize that when I take a two-phase mixture, draw a line connecting the composition of the two phases, and choose the amounts of the two phases so that my overall composition is x, I can show that the free energy just moves up and down this line, just as it did here, the dotted line. Well, the lowest value I can get to is not pure alpha. It's down here. It's a mixture of alpha and beta, where alpha has the composition x alpha in the figure, and beta has the composition x beta. The rule, the graphical rule, that gives me the compositions of the two phases that are present, and their mole fractions ultimately, is called the common tangent rule. Now, all I have to do, if I know these two free energy curves, if I can find a common tangent, a tangent line that touches both the alpha phase and the beta phase, then I do prefer to have a two-phase mixture. Not only that, the two-phase mixture will be such that the composition of the alpha phase is where the common tangent touches the alpha curve, the composition of the beta phase is where the common tangent touches the beta phase. So if I know these two curves, I can immediately say, let me take my composition here, let me draw a tangent to the curve. Does that tangent cut the free energy surface of any other phase? Look up top here, where the common tangent of x, it does not cut any other phase. So here, my situation is that my minimum free energy will give me 100% alpha phase at composition x. Down here, if I were to draw a tangent to the alpha phase, it does cut the free energy curve for another phase. That tells me that my equilibrium situation will be two phases, and those two phases will be determined by the common tangent. Composition of alpha where the common tangent cuts the alpha curve, composition of beta where the common tangent cuts the beta curve. And that will give you a two-phase situation. Another way to look at that is remember that this slope of this curve is the chemical potential. If I have two things, if I have a system that's in equilibrium, it's a condition of equilibrium, the chemical potential will be the same everywhere. That means that if I have two phases in equilibrium, they must both have the same chemical potential. That means the tangent must be the same. And that condition is satisfied by the common tangent rule, because down here, the tangent to alpha phase, chemical potential of alpha, is precisely the same as the tangent to the beta phase, the chemical potential of beta. So in summary, if I have this situation, a B binary compound that has two phases, alpha and beta, with these two free energy curves, and I ask what is the preferred phase going to be and what is its composition going to be, if I start out with pure A and I move in this direction, for all compositions x less than this x alpha, which is at the end of the common tangent, my preferred situation would have only alpha phase, 100% alpha. Starting with B and going in this direction, whenever the composition is greater than x beta, the common tangent, then my preferred situation is 100% beta over here. In between this concentration x alpha and x beta, which is determined by the common tangent, my preferred state is a two-phase mixture of alpha and beta, where whatever my composition is, the alpha phase has concentration x alpha, the beta phase has composition x beta. And that's what determines the phase diagram at the particular temperature that is represented by this diagram right here. Well, so phases in a two-component system, here's just some other examples. Look at the gamma phase up here. And we say, here's our, at a given temperature, here's our free energy versus x plot for an AB binary solution that has alpha, beta, and gamma as possible phases. You draw a common tangent. The common tangent to alpha and beta never touches. I'm sorry, to alpha and, see, this is beta and this is gamma here. It's kind of confusing in the figure. The common tangent to alpha and beta never touches the gamma phase, never touches the red curve here. So what do we have? Starting at alpha, we have 100% alpha phase until we get to concentration x alpha. We then have a two-phase mixture, x alpha and x alpha with concentration x alpha, beta with concentration x beta, until we get to x beta. Then we have all beta from then on out to pure B. The gamma phase never appears. But now let us suppose a slightly different situation. Suppose now that the gamma free energy curve is a bit lower, so that a common tangent between alpha and beta passes through the gamma phase. In that case, the lowest free energy is determined by common tangents between alpha and gamma and beta. And now we will get alpha until concentration x1, a mixture of alpha and gamma phases between x1 and x2 in the figure, gamma phase between x2 and x3, beta plus gamma between x3 and x4, and then beta when the concentration is greater than x4. So everything is determined. If we know the free energy curves, everything is determined by these common tangents. And the phases that appear are the phases that are connected by the common tangents of least energy, least free energy. All right, we're going to talk about, oh gosh, this should be alpha. I'm going to talk about two phase diagrams that only, well, here's what I want you to do. I'm going to want you to understand two phase diagrams. How do the free energy curve generate those phase diagrams? The two I'm going to want you to understand are the phase diagram for two elements that form solid solutions at all compositions, and the phase diagram for two phases that have the eutectic reaction, form what we call the eutectic phase diagram. These I'm going to want you to understand, so we'll go through how free energy curves will give us these two phase diagrams. But in addition, I want you to know how to read any binary phase diagram at all. The binary phase diagram is a map. What it shows are the phases present at given values of the temperature and composition. From that, you can tell, from a phase diagram, you can get three pieces of information. You can get the phases present, you can get the concentrations of those phases, and you can get the fractions of those phases. And that's what we will learn in how to read a phase diagram. Then I want you to specifically learn the solid solution phase diagram, the eutectic phase diagram, and of course how to read any binary phase diagram. And having said that's what we're going to do, we're now out of time, so we're going to do that on Friday.